Hello and welcome. In this video, we're going to talk about how to add, subtract, and multiply polynomials. And in the following video, we're going to focus on Pascal's triangle and how to expand binomials using a more efficient method. So let's go ahead and jump right in. So in the last video, we talked about what a polynomial was, how to identify that it's in standard form, the degree and the leading coefficient, and what we're going to be doing now is really focusing how to perform operations when we have more than one polynomial expression or we have a series of monomials. So we're going to start by reviewing how to add and subtract polynomials, which is just really a review of the fact that we are allowed to combine like terms. So we need to make sure that we're combining terms that are like or alike, and not terms that aren't. We're going to talk about this in two ways. We're going to talk about sort of what I like to call the old school addition way, where when we first learned how to add, we would stack numbers and we would add the tens column or the hundreds column, and then we would keep adding, and that's how we would get our sum. That same strategy works with polynomials. So you need to make sure that you're lining up your different like terms. So I can see I have my x cubeds here, I have my x squareds here, I have my x's, and it looks like the second part doesn't have an x term, and then I have my constants. And then we're going to go ahead and add up and down. So when I add my constants, I get positive 1, negative x plus nothing is negative x, 2x squared plus negative 10x is going to be negative 8x squared, and 3x cubed plus x cubed is going to be 4x cubed. And remember, when we're adding, we're really counting how many we have. So the exponents are not going to change. X cubed plus x cubed is 2x cubes. We've also done questions like number 2 in previous classes and in this class. So it's not stacked vertically, which you're more than welcome to do. You could rewrite this whole expression underneath that one, and then you could add up and down. Or you can just identify what those like terms are, and I like to do that with highlighters. There is only one term that has a cubed, and that's 9, so 9x cubed. Then I'm going to find my squared terms. I have 3y squared, and I have negative 5y squared. If I add those two things together, I'm going to get negative 2y squared. Again, not changing that exponent. If I look at my x's, my terms that just have, or I guess in this case y, I have negative 2y and positive y. If I combine those, I'm going to get negative y. And then I'm going to look at my constants. If I combine 1 and negative 4, I'm going to get negative 3. So notice when I'm doing this, I'm keeping it in standard form, because then if I was asked to talk about the degree or the leading coefficient, it would be easy to identify that from the first term. Let's talk about the slight difference when we're subtracting. When we are subtracting, we need to make sure that we appropriately deal with our negative sign. So in the last chapter, we were adding and subtracting real and imaginary numbers, and I wanted to make sure to point out that it's always going to benefit you to distribute that negative sign first. And when you try to do the math without distributing the negative sign, most of the time you're going to make a mistake, not because you don't know how to do it, but because you're trying to skip too many steps. So don't skip that first step where you distribute the negative. So I'm actually going to do number 4 first. I'm going to distribute the negative. So that's going to become, the first part's going to stay the same, 2z squared plus 3z. 3z squared is going to become negative. Z is going to become negative, and negative 4 is going to become positive. And now I can do exactly what I just did. Now that I've dealt with the negative sign, I can just combine like terms here. So 2z squared and negative 3z squared, when I add those together, I'm going to get negative z squared. When I combine negative z and 3z, I'm going to get plus 2z. And that 4 is the only constant that there is, so when I put that at the end, I'm going to have that. So here I have a polynomial, degree 2, leading coefficient, negative 1. Now you can also do this the stacking way. I still recommend that you rewrite it as an addition problem. So keeping the top line the same, and then changing the sign on that second line. So negative 2x to the third minus 6x squared plus x minus 1. And then you add. Distributing the negative first just gives you less room for error. So if I combine up and down here, 8 and negative 2 is going to be positive 6. Negative 3 and negative 6 is going to be negative 9. Negative 2 and positive 1 is going to be negative x. And then 9 minus 1 is going to give me plus 8. So that's a little review on adding and subtracting with polynomials. Now let's talk about multiplying with polynomials. When we multiply with polynomials, we need to make sure we multiply each term by each other term. And I want to remind you some rules of exponents. When we multiply two terms with the same base, we add the exponent. So if I was multiplying x squared times x to the third, that would become x to the fifth. So we need to make sure we acknowledge the exponents are going to change now because we're changing the dimension when we multiply. The base is going to stay the same, but that exponent is going to change, and we're going to add those exponents. So most of you have done multiplication with polynomials in some way like this. And when we teach this, we usually teach the distributive method, meaning that you could take y and you could multiply it by this entire polynomial. So y times 3y squared minus 2y plus 2. And you can add that to 5 times that exact same polynomial, 3y squared minus 2y plus 2. Some people just do it with the arrows. I like to show that one step ahead of time. So then now we can distribute. If we multiply y by 3y squared, we get 3y to the third because the exponents 1 and 2 add to be 3. If we multiply y by 2y, negative 2y, we get negative 2y squared. If we multiply y by 2, we get 2y. 5 times 3y squared is going to give us 15y squared minus 10y plus 10. And now we're going to go ahead and combine like terms again. 3y squared is the only term 3y cubed is the only term that's cubed. We have two squared terms that we can combine to be 13y squared. And then we have 2y and negative 10y, which will give us negative 8y. And then we have our constant plus 10. Also in Algebra 1, you often learn the area model or the box method for multiplication. So we could say y plus 5 times 3y squared plus minus 2y plus 2. And then we can multiply sort of like the Punnett square inside the box. This thing times this thing, 3y squared times y is 3y cubed. In this box, negative 2y times y is negative 2y squared. Y times 2 is 2y. 15y squared, negative 10y, positive 10. And then you can combine like terms and get back to this same polynomial expression. So all of those strategies still work. You sort of need to pick what you are the most comfortable with and what works for you. But I want to show another strategy that maybe you haven't seen before, and it ties back to when we first learned how to multiply a two-digit number by a different number. So we would take the 4 and we would multiply it by 2 to get 8. We'd multiply it by 5 to get 20. We'd multiply it by 1 and then add that 2 to get 6. And then we would put in a placeholder and we would do the same thing with the 2. 2 times 2 is 4. 2 times 5 is 10. 2 times 1 is 2, and then we would have that placeholder, and then we would add up and down. So that's where this strategy is going to come from. This strategy comes from the idea of doing what we first learned how to do when we were multiplying bigger numbers together. The thing that some people like about this is that it makes it easier to combine like terms, and that's a great strategy. Again, my goal is to teach you a variety of ways and for you to decide what works best for you. So I'm going to multiply my 3 by 4, by 2x, and by negative x squared, and I'm going to write that along this spot. Then I'm going to go back and multiply x by 4, and x by 2x, and x by negative x squared. All right, so 4 times 3 is negative 12. Negative 3 times 2x is going to be negative 6x. Negative 3 times negative x squared is going to be positive 3x squared. So I have dealt with the top row. Now I'm going to deal with the bottom. I'm going to put a placeholder here. X times 4 is going to give me 4x. X times 2 is going to give me 2x squared. X times negative x squared is going to give me negative x cubed. Now everything is nicely stacked, so I can just add up and down. Negative x cubed plus 5x squared minus 2x minus 12. And there's my polynomial expression. So play around with these different methods and decide what works best for you. But I want you to try each of those methods to kind of get a feel for it. So let's look at 2 more examples. All right, I want you to go ahead and pause the video and work through these 2 examples on your own, and then unpause the video and see how you did. So hopefully you had time to work through those examples and to combine like terms afterwards, and hopefully you're getting an idea of what works best for you. So what happens if instead of multiplying 2 things together, we're going to multiply 3 things together? Let's look at that next. Okay. If we have to multiply more than 2 binomials together, we can do that in any order that we want to, just like if we were multiplying integers. 2 times 3 times 5 is the same thing as 6 times 5, which is 30. The same concept exists here. So what I'm going to do is I'm going to go ahead and multiply these first 2 together. If I multiply them together, I'm going to get x squared minus x plus 4x, so plus 3x minus 4, and then that still needs to be multiplied by this term here. Then I can go ahead and multiply this out. This is going to give me x to the third plus 5x squared plus 3x squared plus 15x minus 4x plus 20. And I can combine like terms, so I'm going to have x to the third plus 8x squared plus 11x plus 20. So the order that you multiply in doesn't matter. It just matters that you're multiplying all the way through to get this entire product expanded out as a polynomial instead of as the product of binomials. All right, I'm going to encourage you to pause the video and multiply out number 10, and then unpause the video and see how you did. So if I expand those first 2 binomials out, I get x squared plus x minus 2, and then I can go ahead and distribute or expand out the 2 polynomials I have left, that product, and that's going to get me here. And then if I combine like terms, I'm going to get x to the third minus 2x squared minus 5x plus 6. This is the product of these 3 binomials. So just take it one step at a time. Again, you're more than welcome to use the box to multiply out if you prefer, or to line them up vertically and then multiply that product through as well. Pick the strategy that works best for you. All right, we're going to talk about a few special product patterns, and then we're going to wrap up this video. So in Algebra 1, we learned about the difference of squares and that relationship, and we reviewed that in this class as well. And what that says is if I'm multiplying 2 binomials that are exactly the same but opposite in sign, that's called the difference of squares. And when I expand that, I end up with just the first term squared minus the second term squared, because the 2 middle terms would add to be 0. So you're allowed to use this rule to jump from here to here without necessarily having to expand. Use that recognition, that pattern, to your benefit. If we're squaring a binomial, there's a pattern here as well. Y plus 4 squared is the same thing as y squared plus 8y plus 16. If you know this shortcut, it can make the multiplication faster. If you don't know the shortcut, you can just expand it out the long way. It's going to work in the same way. It's just going to take you a little bit longer to get there. The new one that we're going to highlight in Algebra 2 is the cube of a binomial. So if we are cubing a binomial, meaning what we're doing is saying a plus b times a plus b times a plus b, there is a pattern that arises here as well. It's going to be the first term cubed plus 3 times the first term squared times the second term plus 3 times the first term times the second term squared plus the last term squared. This pattern works similarly if we are subtracting, and you can see some examples here, and we're actually going to prove that this works. This is one of those properties that, again, will help you be more efficient, but it's not required that you know this to be successful. It will just make you more efficient. And we're actually going to learn another shortcut in the next video called Pascal's triangle to help us expand if it's degree 4 or 5 or 6, how we can do that. But what I want you to do is you're going to help me out with this proof here. I'm going to have you actually multiply these two things together, and hint, hint, you could use the shortcut up here if you want, and then unpause the video and see if you got the first step correct here. So if I expand this, a plus b times a plus b is going to be a squared plus 2ab plus b squared, if I expand that out. And I haven't yet multiplied this by the third a plus b. Now, if I expand this, and I'm going to encourage you, pause the video and do this part on your own, and then unpause the video and see how you did. Here it is unsimplified. If I just distribute each of those terms, again, you can use the box or the area model if you prefer. And then if I combine like terms here, I'm going to get a cubed plus 3a squared b plus 3ab squared plus b cubed. And I want you to notice something about the exponents. We start with the a cubed term, then we go to the a squared term, then we go to just a, and then our last term doesn't have an a. Then we do the reverse with our b's. We start with no b, then we have b to the first, then we have b to the second, and then we have our b cubed term. That's not a coincidence. But you actually just did a proof. We just proved that a plus b squared is equal to this, which is what we had up here. Kind of cool. All right, let's apply these properties to three last examples. All right, here you go. If you recognize the special pattern, go ahead and multiply these out using that rule. If you don't, that's okay. Go ahead and expand it out the long way, and then unpause the video to see how you did. All right, number 11 is the difference of squares. That's going to give me 16n squared minus 25. Number 12 is the sum of perfect squares. So the first term is going to be what I get when I multiply 9y times 9y. The second term, or the middle term, is going to be what I get when I multiply 9y by 2, and then I double it because I would get that 2 times if I was expanding. So that's going to be minus 36y. And the last term is going to be what I would get if I square negative 2, which is positive 4. And then for number 13, according to the rule, my first term should be what I get when I cube both of those. My second term should be 3 times what I get when I square those two times 4. Let me give us some more space here. There we go. So this is going to simplify. I'm going to rewrite this. This second term is going to simplify to be 12a squared b squared. The third term is going to be what I get if I multiply 3 by this term to the first power by this term squared. That's going to be 4 squared is 16 times 3 is 48, so 48ab. And then my last term is going to be if I just cube this last term, 4 to the third power is going to be 64. So here is my expansion of ab plus 4 quantity cubed. So key things that we covered in this section. We reviewed how to add, subtract, and multiply polynomials. We talked about doing it sort of old school where we stack things. We talked about doing it using the area model or just combining like terms. You need to decide what works best for you. Then we extended this idea a little bit by multiplying, instead of just 2 polynomials, 3 polynomials. We derived the perfect cube product, and we worked through some other examples with special products. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.